In this video, I want to have a look at algebraic manipulation of matrices, essentially rearranging things where we're using a symbol to represent a matrix rather than looking at the detail of individual matrices. So we're doing this as a very general kind of process. Think of this rather like changing the subject of a formula or normal algebraic rearranging processes, that kind of thing. I think it's important to have seen these laws of matrix algebra. The ideas here are the important thing rather than the language that I've used. Those words that I've used in italics here are about being commutative or associative or distributive. It's not important that you know those words. It's more that the ideas behind them are the important ones. Just to run through them quickly, these are things that you may well not have even you might not have consciously been aware of when you've been dealing with normal real numbers or the algebra associated with real numbers, because they're just so natural, you just kind of assume them. But now we're dealing with something which is not behaving in the same kind of way as normal numbers, normal real numbers. And so we need to just rethink about some of these assumptions, these underlying assumptions. So the very first one there, addition being commutative, very much like real numbers. It doesn't matter which order you add real numbers together. In the same way, it doesn't matter which order you add together matrices, assuming that you can do it at all. And that's going to be an underlying assumption for all of these things. If we can do the result, then this is the result that we need to, this is the rule about how we need to apply it. So we're going to assume that these things are possible at least. So we can add them together in either order, but we can't multiply them together in any order. This is a really important one here. Multiplication is not commutative. A times B is not, in general, the same as B times A. It might be possible to do A times B and not possible to do B times A, but even if both AB and BA are possible, they may well, in general, they won't give you the same answer. Just occasionally, in very special cases, they will give you the same answer, but generally speaking, they won't. And then we have associativity. This is about if you have more than two of the things, either to add or multiply together. Both addition and multiplication are associative. It doesn't matter if you have three of them. It doesn't matter what order you pair them up, essentially, is what we're talking about here, really. As you can see from the results there, if I want to add three, A and B and C together, I can either do A plus B first and then add C, or I can do B plus C first and then add that to A. Multiplication, you need to be a little bit careful with the associativity of multiplication because the order still has to be correct in terms of left-right. So I can do AB first and then right multiply, or post multiply as it's sometimes called by C, or I can do BC first and then, as long as I left multiply the result of that by A, or sometimes called pre-multiply it by A. So we need to be distinguishing, and so we can't necessarily just talk about multiplication. We need to really be distinguishing between what's either called left multiplying or pre-multiplying, if it's on the left, or right multiplying or post-multiplying, because those two things are different in general in matrices. Distributivity, the fifth law, is about expanding brackets, and that behaves exactly as the normal process of expanding brackets, either by a scalar or by another matrix, as long, again, as you remember the non-commutativity of multiplication. So A times brackets B plus C close brackets can be equally well calculated by doing A times B and then adding A times C, but you must keep the order the same. So I couldn't, for example, do B times A plus C times A there, or even A times B plus C times A, or B times A plus A times C. The order has to be correct. The B and C are both being left multiplied in my example there by A. And so each of them separately has to be left multiplied by A as well. This has a particular effect in expanding a square bracket, as you can see in my example here. It's exactly the same as multiplying out, expanding a real number square bracket, except for this last stage where I have the two terms in the middle, AB and BA. I can't combine those. I can't collect those into a single term to AB because AB is not, in general, the same as BA. So I can't do that last step of taking it down from 4 terms down to 3 terms. I have to keep those two in the middle separate. So those are your essential laws. A quick word about identities and inverses, and this in particular really only applies really to square matrices, and I'm only going to be dealing with 2 by 2 square matrices. You might well have to do this with 3 by 3 matrices, but that's okay. It's the same rules, just for the sake of keeping it fairly straightforward at the moment. I just want you to be imagining these as 2 by 2 matrices. And of course, you know that not every 2 by 2 matrix can be inverted. You have singular 2 by 2 matrices. If the determinant is 0, you can't invert it. So we're going to assume for the rest of this that if we're talking about an inverse matrix, then it is possible to invert the original matrix. But these are 3 important laws about identities and inverses. The point of an identity matrix is that I can multiply a matrix either on the right or on the left by the identity matrix of the same size, and it doesn't have any effect. Essentially, an identity matrix behaves like the real number 1 in multiplication. It doesn't have any effect. And then inverses, it doesn't matter whether you right multiply or left multiply a matrix by its inverse, the result will still be the identity matrix. That's the point of it. And as a consequence of that, this also means that the inverse of an inverse matrix is the original matrix. A to the minus 1 to the minus 1 takes you back to the original A. And anything else apart from those things that we've discussed so far needs to be proved. Any of these can be assumed. You can assume any of those things, those 5 things there, or the business of expanding a square bracket or using identities and inverses. Any of that can just be assumed knowledge now. But anything else needs to be proved before it's used, certainly for an exam at least. There are several other commonly used results, but I wouldn't feel comfortable about advising you to use them in an exam without proving them. For the worked example here is one good example. This is a commonly used result, but I would be uncomfortable about anybody quoting that result in an exam without proving it. So I think you should. And I want to just take you through the proof of that here. And then you can see there's a little exercise of some. Hopefully my worked example will give you some ideas about how to approach the questions in the exercise there as well. So you should take these really essentially as being very much like algebraic manipulation of formulas, equations, rearranging things, solving equations, that kind of thing. And as long as we remember the laws that we've got for matrices, the process is basically the same. The big, really glaring, standout difference here is that I can't do any division. It's not defined. What we mean by dividing by a matrix, we don't know. And instead of doing that, what we have to do is multiplying by an inverse matrix. It's really the point of an inverse matrix. So if you think about it in that kind of way, hopefully the process becomes a little more straightforward. Let's take this worked example one here. We want to prove that AB to the minus 1 is the same as B to the minus 1, A to the minus 1. So look and see how that's working there. I've got the inverses. If I want to inverse things separately, I need to also reorder the multiplication compared with the multiplication before I've inverted it. That's the point here, really. And the proof of this goes something like this. So if I take that product AB and then invert it, ab to the minus 1. What it means is that if I multiply the inverse by the original product, I should just get the identity matrix. That's the point of an inverse, isn't it? So, and now we have this business here about the associativity, this one here, of multiplication. I've just got three things being multiplied together on the left of this, the inverse of AB multiplying A and B. And so the brackets around the AB, not the inverted bit, but the second brackets, you can see here, are not really, strictly speaking, necessary, because it doesn't matter what order I do these three multiplications as long as I keep them left-right the same. So I can just remove that second pair of brackets there without altering anything at all. And now what I would like to do really is to strip away any of the things that I don't want. I want a result which is telling me something about AB to the minus 1. So I want to strip away the A and the B here. And if this was normal algebra, I would be dividing by A and B. I can't do that, so I need to be multiplying by an inverse where I would otherwise be dividing. And I've got to make sure I do it in the right order as well. Now, the B is at the end there. If I was to stick a B to the minus 1 on the end of it, it would be next to that B, and then I can use my result about them being the the pair of them, being replaced by I. So I can do right multiplying by B to the minus 1 as long as I right multiply the other side by B minus 1 as well, like that. Okay, and now I can start to use some results. I can put a pair of brackets around the B minus 1 there. And that's not going to change anything at all. And now I can just simplify the line that I've got here a little bit. So I don't want to change the AB to the minus 1. The A is going to have to stay there, but the B times B to the minus 1 can get replaced by an identity matrix there. And this B to the minus, the right-hand side of my equation here, the B to the minus 1 is being multiplied by the identity matrix, so it's not going to change it. So I can just keep that as B to the minus 1. And actually, I can also get rid of the identity matrix on the left as well, can't I? So AB to the minus 1 times A must be the same as B to the minus 1. Now I'd quite like to get rid of that A as well. So I can, if I right multiply by A to the minus 1, that would be the alternative equivalent to dividing by A, and that would remove it from that side. So if I'm right multiplying by A to the minus 1 on the left of my equation, I also have to right multiply on the right-hand side of my equation, B to the minus 1, A to the minus 1. Hopefully you can see where this is going now. So those two things there can get bracketed together, and they can get replaced by an identity matrix. I, and then I can remove the I because all it's doing is multiplying a pre-existing result, and therefore it won't change it. And there's the result we're looking for. So hopefully that gives you some clues about how the process of these sorts of proofs work. Really, it's just about making sure you're careful with the side that you're multiplying on, left or right, and then instead of doing any division, multiplying by an inverse matrix.